Welcome to our presentation, continuing on our RIST theme this morning, talking about reliable internet stream transport. We have Adi Rozenberg from AlvaLinks Limited, and Adi's going to be giving us a presentation about RIST source adaptation. So, take it away, Adi.
Thank you, Wes. It's great to be here after 2 years. So, my name is Adi Rozenberg. I'm the founder of AlvaLinks, and I'm also a contributor to the RIST activity group and the RIST specification. Today, I'm going to talk about something exciting that everybody has to be excited. I'm surprised that there are not thousands of people hearing about that, but they'll probably hear it later. So let's go. What is the story with adaptivity? Most delivery protocols assume that the link capacity has enough capacity to support the stream and some extra headroom for ARQ retransmission and such. Most networks do have their quirkiness events. Oversubscription, sudden high interferences, capacity drops, link saturation that we will need to overcome. HTTP adaptive streaming, also known as HLS or DASH, show the world that you can overcome these problems by way of using different profiles that you can switch between them. But then that adds extra latency, and it's not usable for low latency delivery. How do we bring the same concept for low delay transmission and take these challenges head on, still while deploying the lowest delay possible? So first, let's talk about the pillars of reliable delivery. On the bottom, we see the jitter suppression, error removal. We have RIST to do that. We have security that we see in the previous presentation, talking about AES. RIST also give us DTLS, PSK. We have path diversity multi-link that we can use, and we have loader. Those were available and are available in the RIST simple profile, RIST main profile, and some other protocols that try to do the same. What is missing is the top of the pyramid, the holy grail, the adaptivity. How do we adapt? So let's see, why do we need to do that? So imagine this. We have a link in gray. We have a capacity. Somebody tells us it has 12 megabits. We have our stream in blue. It has 10 megabits. We test that for 10 seconds, 5 minutes, 2 days. Everything is fine. We start streaming, but then something along the way, AWS crashes, my ISP has a link capacity issues, the link drops, and on the other end, instead of getting a blue line, we get something orange, which is crappy, and no ARQ can fix that because we don't have the capacity to allow it to switch. What we need to do is to provide adaptivity, basically detect those conditions, squeeze our content or use a different link so that we can pass through that and get to the other end. So the service will continue. So let's go forward. So source adaptation support is a part of the new RIST TR-06-04 Part 1. And it's going to add these capabilities to existing protocols, which are the simple profile TR-06-01. It will also be adopted by the TR-06-02 by way of that it is conveying the simple profile in its capability. And the new and exciting protocol, which is the TR-06-03 advanced profile, and it has a specific control message specifically for that. Today we're going to highlight two cases. One is adaptive source control, and the other one is adaptive multipath delivery. So let's see let's go down to the bits. So we have a message. We have basically a new message, a receiver report going from the receiver back to the sender, giving it new statistics that were not there before. We have sequence number, so we can know the message, we can follow and track that. We have a reporting window that says, hey, this is the window that this report is all about. A NAC window for the error correction, and then counts, a lot of statistics that gives us the information that we need. Count of the source packet received, count of the source packet lost, how many packets were not received, which are original packets, meaning not retransmitted packet. Count of retransmitted packets that were received, how many packets we did able to recover during that period, how many packets we couldn't recover in that period. It is specific to the period, not to the whole 24 hours and beyond. We also get a count of delayed packets, so maybe that gives us more information about packets that are coming too late. We also get information about the data bandwidth and the measured retransmission bandwidth, so we get a broader view of what is going on the link. We can sense, for the first time, a protocol gives us information, vital information, to understand what is going on my link and what should I do about it. It's a very important piece of information that we as senders or users should have. So this is the explanation of what is there. I'm not going to go about this. I just explained that before. So why do we need this capability? As I said, link behavior may change during an event, day, or over time. Sudden error recovery is not designed to overcome link capacity errors. Some links may be limited with error correction capacity, and respreading the system, the stream between more links will be much more desirable than what we are used to do today. Sometimes all we are left with is to command the source to change its compression or change its components. For example, we can take out an audio component or an auxiliary data component, but allow the video to pass through if we so desire. We strive to the highest quality and not to drop the lowest, and not to drop to the lowest possible capability. So let's see a standard RIST simple and main profile load share example. We'll start with that. In this example, I have a RIST sender. It has 3 links connected to a RIST receiver. So we have like 3 ISPs that we will going to use. So until now what we have is that in a simple profile example, we have RTCP messages, and they are giving us information about jitter and somewhat bandwidth. But they are very generic and not specific to a period of time. So I have no statistic about every link going through. No statistic on ISPA, no statistic on link B, and I definitely have no statistic on ISPC. These are missing. Now we want to change that. So let's see receiver reports. We have the same system, but now you can see statistics. We can now provide statistics on path A, B, and C. So now the sender has more information about every link. And also something that's not seen here is that it also has the information about the entire stream, not only on the link themselves, but the stream as a whole. So he can decide to use AI algorithm to spread around the joy of the streaming between those available links. So let's see an example. So in this example, we start with a spread of 30% will go over ISPA, 30% on ISPB, 40% on ISPC. That is how we decided to do. We don't know the bandwidth, but that is our initial decision. So we start. We sent a report over stream C, everything is okay. But suddenly there is a report saying there are unrecovered packets on stream C, on ISP-C. What we should do about that? If they are created unrecovered packet, means that there is a problem and we cannot fix that. So we will recalculate the load, the spread of the bandwidth between the links. We will change the ratio, And now the system decides, based on the information, to change that. Send 20% on link C, and I increase link B and link A to have more bandwidth because they show a good solution, no problem, and everything is well. So we fixed the problem. We recalculated the load and we fixed the problem. So basically the outcome coming back, we see that link C reports non-recovered. We don't need to do anything. The stream goes through. Everybody are happy. No more interference. We solved the problem. We adapted to the condition. And that is done. It can be done every 50 milliseconds, 100 milliseconds. So it's much more agile, much more adaptive to the condition as they change immediately and not after a minute or so. You don't need human intervention here. The algorithm that implemented by the equipment manufacturer or RIST implementation will solve you the problem. Now let's see the next use case, which is source adaptation. In this case, we have an encoder. The encoder is controlled by a RIST sender, and it can command him to change its bitrate to the network condition. In this example, we will start with a 10 megabit stream. We will command it start sending a 10 megabit stream to the other end. Everything fine and dandy, everything is good. We are okay. After statistics are flowing through, everything is okay. We don't need to change anything. Now we send the 10 megabit stream through the ISP, but suddenly it only appears as 4 megabits. Well, something is wrong. We send 10 megabits, we're receiving only 4, and we don't have a bandwidth. We need to change that. Error correction doesn't work. So we send, basically the statistics give us a hint that the rate was dropped and the packet lost, unrecovered. So the sender will now think about it, ponder about it. I need to calculate the rate that can be used. So, well, I can probably do 4 megabits. So let's set the encoder to 4 megabits. Let's see what that will do to us. So we send the 4 megabit and it goes fine. Hey, we adapted. We changed. We send the 4 megabit and it passed through and everything is fine. But now, do we want to stay at the 4 megabits? The answer is no. We want to change back. We want to increase the quality. So let's try to change to 5 megabits and see what happens. So we now command the encoder, hey man, change the rate to 5 megabits. So the encoder acknowledges that and gets set 5 megabits, sends that through. So now the receiver sees 5 megabits and he sends a report. And it says rate is okay, I received 5 megabits, I have no problems, everything is fine. We adapted. And then that can go on and on constantly. So we adapt to the link. So the next question is, what else can I do with this new and found technology? We can select, inspect what is the best available source, whether I have Wi-Fi, wireless LAN, 5G, maybe a Starlink. If those are available to me, I will check the link and I will adjust as much as I want. I can deploy more capabilities, more streaming, reliable streaming, so that no impact will come to the stream. We can partition the stream between different paths. We can send audio on one end, video on another one, and auxiliary data on another one. We can gather, we can send more information as we want. We can send several services. We take a transport stream, take some of the services on path A, some of the services on path B, the audio on path C, and RIST will re-aggregate that to the stream at the other end. That is the benefit of RIST. So let's see that, some ideas. Stream partition, as I said, we can take high priority services on the most reliable link, low priority services on less reliable string, and we have a working solution. We can take, as I said, components and video stream on the lowest delay. Let's say we want to go to the cloud. Let's assume that we have a ST2110. We will send only the video portion on the lowest delay link, but the audio we can send over the regular internet because audio can tolerate the delay necessary. We are sending less information, causing less problems when you go over the network. The receiver statistics for before and during the transmission will provide better results and overall continuity of service that was not there before. Before it was a guessing game. Now we are in full control of what is going on. It's a bright new future for everybody. Is that all? Well, we have more information in our hands, right? Suddenly we have link statistics that we can share that. We have RTT report, RTT capability, jitter reports available through our TCP. We have a broader view of what is going on. We can share that with our DevOps, with our IT organization, and the network provider, so we can say, hey man, you had a problem, we took care of that, but you should go and fix that because we will not tolerate the drop of bitrate. We prayed for 100 megabits, we expect to get 100 megabits and not drop to 40 megabits from time to time. You have that statistics. You can put that in your monitoring system and have a better visibility. You can have a better visibility how the data is traveling and received at the destination to allow you to react and change your behavior. A smart implementation will take the handle, the helm, and do an autopilot for you. Just as we expect the Tesla tunnels to allow us to do self-driving, now with this information we can react and adjust ourselves as we pass through whatever links are available to us. And that is the end of my presentation. Any questions?
Okay, I'm going to ask you a question. You can say, you can decline to answer. Can you comment on any IPR issues on your presentation on implementing that?
So, not Internet Protocol reboot, it's intellectual property rights, okay.
There are certain IPR issues with source adaptation. Those who have questions can come to me. Apparently I hold some patents on this technology, but they are to do with the source, with the encoder adaptation, but link adaptation, it's a freebie. It's a part of the RIST, so there's no problem with that.
Okay, thank you very much, Adi. We appreciate it.